In this problem, we want to find the approximate area bounded by these two functions. And the issue there, the reason why it says approximate, is that the intersection of the two functions has to be approximated using technology. So that's the first thing I'm going to do, is just try to figure out what's that intersection x value. So I'm going to use wx maxima for this, and just real quick sort of theoretical justification for what I'm doing. I'm trying to find out where these two functions are equal, so I set them equal. And then I would be able to solve for the x that made the two y values equal, which is what we mean by the intersection. So maxima can't do that directly, but what it can do is give you an approximate value where a function is equal to 0. And a 0 of a function is called a root, and this algorithm is called find root. So I'm going to go find root 0.5 times x minus sine of x, and then you have to give an interval in which you think the root may occur. We could tell from the picture that it was somewhere between x equals 1 and 2. Hit shift enter and I get 1.895. That's a good enough approximation for me. So x is approximately 1.895. So that will help when we set up our integral, because it'll give us one of our limits of integration. All right, then I get into the sort of geometric understanding of how to get the area, and the idea is to take thin slices, and then you have to appropriately express the height of the slice. The width of the slice is going to be a little dx, and the height is going to be, you have to think about which of these curves is on top, so I get a positive height. So the sine function is on top, so the height is sine x minus 1/2 x. Okay. Then I try to get an expression for this differential contribution to the area. dA is equal to sine x minus 1/2 x multiplied by the width of the little rectangle dx, so that's just height times width. And then the total area is the sum of all those area contributions. So a really useful way to think of an integral is as a summation device for summing infinitely many infinitesimal contributions. Now I can write down the total area as sine x minus 1/2 x dx. These two functions intersect first at x equals 0. I can see by plugging in 0 here that they definitely intersect there. And then they have their second intersection at this approximate value of 1.895. So if I'm already approximating, then you might argue that it's fair to just use maxima to do the integral, but the integral isn't too bad, so I'm just going to do it by hand. So I get negative cosine x, and then minus 1/4 x squared, evaluated from 0 to 1.895. I plug in the upper limit, and I get negative cosine 1.895 minus 1/4, 1.895 squared, minus what I get in the lower limit. So the minus is going to put a plus on both of these, and when I plug in 0, I get cosine of 0, that's plus 1. And then this term vanishes when I plug in 0 for x. And now it's calculator time. Unfortunately, I don't have my calculator program running right now, so I have to use a real one. And here we go. So I had to set my calculator in radians. If you're just doing physics or something, you might be set in degrees. All right, and I get 0.42-ish for this. I should really indicate that it's an approximation. So 0.42 is our approximate area.